Thank you, everyone. It's an honor to be here, and thank you for receiving my presentation. Slides, please. I'm starting with this star-studded sky, which you'll see in a second, from a mountaintop in Hawaii, to remind all of us that the stars are for everyone. And also that all stars are suns, and if our sun has planets, surely other stars should also, and they do. And we call these planets that orbit other stars exoplanets. We know of thousands of exoplanets right now, and evidence appears that every star should have planets. Now, it turns out our own solar system is very hard to find. It's very difficult to find. It may be rare, in fact. So instead of finding planets like the ones in our solar system, we're finding all sorts of crazy planets, like a Jupiter, where an Earth should be. Some planets the size or mass of Earth are so close to the star, by Kepler's law, their year, the time it takes them to go around the star, is less than 1 day. And their surfaces will be so hot, it's hot enough to melt rock, and there will be liquid lava. I actually did spend the whole 20 minutes telling you about all these different types of amazing planetary systems. But I will tell you that after thousands of years of people wondering about planets around other stars, it turns out that our very nearest star, Proxima Centauri, at 4 light years away, appears to have an Earth-mass planet. So these planets are everywhere, and I'm going to update you on where we're at with planets and the search for life. So the latest is that on April 18th of this year, from Cape Canaveral, Florida, aboard a SpaceX Falcon 9 rocket, NASA's latest planet-finding mission was launched. I'm the Deputy Science Director for this mission. Here's the actual rocket launch that went off. It was a beautiful day, and the plume was just so incredibly bright. And whenever you have a project on a rocket, like your kind of 10 years of or more of your life's work is sitting up there, like in the fairing, and you're just kind of excited, but keeping your fingers crossed that it doesn't blow up. So this mission, essentially, it's not a small satellite like we heard about before, but it's pretty small. There are people to show you the scale. It's about 350 kilograms overall, so it blows away your category for small satellites. In the middle, you can see the solar panels, and at the bottom, there's a big Ka-band antenna for communication. Inside, you see these 4 tubes. Those covers come off, they were just there while building it, but there's cameras inside. Each one is almost like a very specialized telephoto lens, only of about 10 centimeters in diameter, and they're very specially made to be not sensitive to temperature, and they don't have vignetting or other problems that your old-fashioned camera may have had, and they're attached to detectors that are about 16.8 megapixels each. And the goal of TESS is to find planets. And here is a image of the sky taken by TESS in a 2-second exposure. And this one actually was really just for show, but I just wanted you to see the beauty of the night sky above the blurring effects of Earth's atmosphere. In fact, this image is just a small part of the size of this image, believe it or not, is just one small part of 1 CCD out of the 4 that make up one TESS camera. So each of the 4 cameras has a kind of footprint on the sky of 24 square degrees. And for those of you who are familiar with the constellation Orion, Orion would fit into 1 camera. So this camera is taking up a large part of the sky. And there are 4 cameras, and here it's showing you how each 1-month observation takes up a very large strip of the sky. So this is really new for astronomy, to look at such a large part of the sky at one time. And each of these strips of the sky will be studied for 1 month each, tiling the southern hemisphere first, then the northern hemisphere. So what TESS is trying to do, like other missions before it, is look for planets that have a chance alignment to go in front of their star as seen by the telescope. Here you're seeing on the top an image, like a fake image of our sun with a planet. And that particular planet, by the way, happens to be the size of Earth in this illustration. And on the bottom is what we observe. We're watching the star's brightness as a function of time. And when the planet goes in front of the starlight drops by a tiny, tiny amount. And that amount is in relation to the area of the planet to star. And TESS, you saw all the stars in the wide field of view. TESS will be monitoring literally hundreds of thousands of stars at once, with a special focus on 20,000 stars, because we can't downlink all those images every time. We have a real data rate limitation. So we make specialized windows around stars of interest and just downlink those. But this is the main way that planets are found today. And it turns out that each one of these little drops in brightness, it could be a planet, it could also be a star or instrument systematics. So just finding this is just the first of a long series of steps where astronomers literally all around the world will be following up the signals to see if they're a planet or something else. And I want you to know okay, so here I just wanted to show you some real data. And the picture on the left are just the pixels, because of the lit up pixels by the star. And on the right, you can see 3 rows. The first row is raw data. There, the star, as brightness as a function of time, doesn't look very stable, but there's a lot of instrumental effects that get removed, and eventually you get to this middle one where you see the transit, the drop in brightness happening 5 different times in that image. And then at the bottom is the so-called bin data. But the point I want to make to you is that, like, my team right now, like literally, not right now, but when they have, when it's their business hours back at MIT, they're finding planets today. And so it's actually just a standard part of everyday science now to be able to find planets or planet candidates around all of these distant stars. So I wanted just to pause for a moment for you to imagine that there is a planet not too far away with intelligent life building the kind of telescopes we have. And they're there telling you, oh, today we found this planet, it may be a planet, it may not, and that could have been our planet, transiting our star. So there's just so many planets out there. We're trying to make sense of them all. Now, we did have a question about stamp collecting. Science is often we're just finding things without really thinking. But the whole point of this mission test is so that we may find planets around nearby bright stars that we can follow up with other telescopes. If the stars are bright enough, we would like to be able to study the atmosphere of the planets. And I'm showing you now on the left, I'm going to now take a couple of minutes to explain how we study exoplanet atmospheres. So you see in this artist's conception on the left, there's a fake sun and a fake planet with this glowing part of the atmosphere. And believe it or not, when the planet goes in front of the starlight shines through the atmosphere. And I wrote this little equation down with intensity and optical depth just for people who are in the know, but basically the starlight is exponentially attenuated in the atmosphere due to particles in the atmosphere. It could be clouds or hazes or gas molecules. And we can observe the star by itself, and then the star, when the planet is in front of the star, and subtract and find out what's in the planet atmosphere. Now, this is incredibly challenging because the atmosphere is very small as compared to the backdrop of the whole star. It's like the skin of an onion on an onion against the backdrop of like a giant star behind it. But this is kind of the main thing we do now, and right now, astronomers are able to study giant planet atmospheres, so hot planets with very puffy hydrogen atmospheres. And about dozens of them rather, have been observed. It's not like a great science at the moment. We're stuck with Hubble, instruments that weren't designed for exoplanets, but nonetheless, we still make some progress from it. So today, we use the Hubble Space Telescope to study giant exoplanet atmospheres. In the future, we're all waiting for the next Hubble, the next giant telescope in space called the James Webb Space Telescope. And there's a picture of it. It should launch in 2021. And this will enable us to study small transiting planets. And that's the whole raison d'etre, the reason of being for TESS, is to find a lot of these planets whose atmospheres we can study. Now, about the atmosphere for a moment, we've talked about climate on our own planet and how adding parts per million of carbon dioxide is a problem. On these other planets, though, we don't know actually what sets the atmosphere. Why does Earth have its 1 bar atmosphere? We actually don't know that. We may imagine other planets could have double the amount of carbon dioxide or 100 times more. So we need to study atmospheres of these small planets to understand the greenhouse gas components. And just as a little aside for you, just for one little factoid that you may find interesting, is that we did hear from Dr. Benner that we think all planets are born with hydrogen, just because of when planetesimals and asteroids hit the planet, minerals that have hydrogen in them, blow up kind of, and the hydrogen gets released. Because planets appear to come in all sizes and all masses, some of these planets may retain a hydrogen atmosphere if they're massive enough. And did you know that hydrogen would be the most potent greenhouse gas if the surface pressure is high enough. Because unlike molecules, carbon dioxide and water vapor, hydrogen does not have a dipole moment. Its mass, center of mass and center of charge are basically the same. But what it means is that hydrogen, in fact, in a high enough pressure atmosphere, collisions can induce a dipole moment. And that means, believe it or not, it can end up absorbing across most of the spectrum in the near infrared and infrared. So unlike water and methane that have very discrete bands of absorption, now hydrogen could fill in all those intermediate open areas and cause havoc. But it means it's good for exoplanets because it widens the space in which planets may be warm enough to have life when we think about planets at all distances from their host stars. So we're not really sure what to expect right now. Myself and others just generate molecules in the computer, really, and try to see what's going on. So what we really want to do in the future is look for gases in the atmosphere. We'd like to see water to indicate water oceans on an exoplanet because water is needed for all life as we know it. And I'm now going to walk you through some of the gases sort of the concepts in the search for life on another planet right now. The goal is to look for gases that don't belong. And oxygen is our favorite robust biosignature gas. And believe it or not, people have been thinking about oxygen for 80 years as something to look for in another planet. Now, on our planet, plants and photosynthetic bacteria produce oxygen. And we heard that oxygen hasn't been in our atmosphere oxygen fills our atmosphere to 20% by volume. But without plants and photosynthetic bacteria, we would have virtually no oxygen. So there is life elsewhere, and they're building the kind of telescopes we're trying to build, and they look back at our Earth, and they see oxygen. They will wonder, why is there such a reactive gas in the atmosphere? It should be reacting away immediately, unless it's being continually produced. It shouldn't be there at all, and hopefully that we will be able to work through all the different scenarios people are concocting to try to understand whether this oxygen is created by some sort of obscure geophysics or whether it is made by life. But in addition to oxygen, life produces thousands of gases, it turns out. And even in our atmosphere, every gas in our atmosphere, except for the noble gases, every gas to the part per trillion level is made by life, even though it usually has a dominant source that's not life-related. So on our Earth, life produces many other gases like methane and nitrous oxide, and many gases that are actually made by life exploiting potential chemical energy gradients around our planet. Like methanogens, for example, use hydrogen released from rocks at the seafloor, and they use carbon dioxide mixed from our atmosphere. And with a catalyst, they're able to extract energy by making this reaction happen, and they get energy out of it. But unfortunately for life that uses that, anywhere else on the planet, there may be a slightly different temperature and pressure, which enables the reaction to happen naturally. So if life can catalyze it, then the environment can probably make it happen somewhere else as well. And so this kind of gas, these gases are also have many false positives, unfortunately, because nature has the same molecules to work with that life does. Yet, there is another larger number of more complicated molecules, like dimethyl sulfide, and in this picture we have some methanol and methyl chloride. This is forefront out on the right side now, carbonyl sulfide. And life makes more complex molecules, most for unspecified reasons, signaling or hormones, that on Earth at least, they're not made in large quantities, but on another planet they may be, and we may be able to identify them as being complicated and in context with the rest of their atmosphere not belonging. So it turns out that life on Earth produces thousands of molecules in tiny quantities. And we actually, in my group, I won't have time to describe it in detail, but went off on a giant tangent not related to exoplanets to calculate the sea of molecules that populates all of chemical space and think about algorithms to filter them so that we could be prepared to search for and identify gases of any kind that we may see in futuristic exoplanet spectra. And I wish I had more time to get into my favorite topic, but it's a bit premature right now, so I can't really say a lot really concrete about it, only that when you think of chemical space as the space spanned by all possible molecules, you know that small organic molecules alone could exceed 10 to the 60 molecules, and in drug discovery, people create synthetic molecules in their computer, and they take slices through chemical space to try to make some progress in new drugs. And we've started to study chemical space and find patterns in it that out of all the 200,000 unique natural products made by life, there are actually these subsets that life appears to avoid. And my team is now pursuing this in a kind of biochemoinformatics field to see if there may be anything interesting there. So on exoplanets, we can't study atmospheres of small planets yet. And there's one thing that I left out that I wanted you to know, that this whole search for life by TESS and the James Webb Space Telescope and the first planets that we'll be able to study were limited to a kind of somewhat, let's call it, corner of parameter space. We're limited to these transiting planets that go in front of the star as seen from Earth. We're also limited to very small stars. There are all sizes of stars out there, in particular these small, cool red dwarf stars. And that is because the annulus of the atmosphere, like the skin of the onion on an onion, it's much easier to study it against the backdrop of a small star compared to a very large star. So at the same time of all this business planet finding and in our computers trying to understand which molecules may be made by life and may survive in an atmosphere and may be detectable, we also make big plans to move forward with more complicated missions to study planets that don't involve transiting planets. And in exoplanets, we also have this saying that the line between what is considered mainstream science, everyday work, planet finding, and the line on the other side for ideas that are completely crazy, that line is constantly shifting. So this new idea has been around since the 1960s, and the idea is to send up a telescope and the Starshade could launch together. It's a very large screen that is stowed in a very special way, and it unfurls from its stowed position, and the central truss expands until the petals snap into place. This Starshade would be tens of meters in diameter, and in order to work, to block out the light of a star, to be able to see a planet directly, it has to formation fly in incredibly precise alignment with the host star so that we could see planets directly. If we want to be able to find the true Earth twins, we must have a way to go to space and to block out the light of a sun-like star to see the planet directly. It turns out that our Earth, in reflected light, is 10 billion times fainter than our sun. So if we want to really get to know the nearest truly Earth-like planets in front of sun-like stars, we have to have a way to do these nearly impossible tasks. The Starshade was conceived in the 1960s. Every decade it's been revisited until recently my team has been able to move it into mainstream science. And there's a lot behind this that I won't have time to get into, but please feel free to ask me about it in the breaks and lunch and over dinner. Here's a picture at the NASA Jet Propulsion Lab, Starshade Lab, where you can see different components, including what is called membrane management of how it would fold up and deploy. Now, just to finish up, I wanted to touch upon the sort of practical value of exoplanets, because there isn't one really. We're here really to inspire people about what is out there, what is beyond our Earth, what is the bigger picture, and what it means for us. Exoplanets encourages people to enter STEM fields. And this is really important because kids, of course, don't know about the quantum Hall effect. They're not really into quantum computing. But the stars and planets really do belong to everybody. It turns out that we had a comment the other day that it's really, recently I testified to the United States Congress, to Senate about space as they're putting together their next NASA authorization bill. And both sides love space. They love exoplanets, they love going to space, and it does help unite us. There is sometimes practical value. And just to tie back to our last talk, I do have my own CubeSat in space right now, and we invented it at MIT, and JPL ultimately built and implemented it. And the goal was to put up a constellation of small telescopes, and each would look at its own very, very bright star, because the brightest stars are spread all around the sky. And we want to monitor one for a transiting planet around a sun-like star. Now, I don't think the constellation will ever happen, but our prototype was able to actually point precisely, more precisely than 100 times better than anything in its mass category. And so the legacy of the project will not be for exoplanets, but it will most likely be for optical communication. When all these great satellites need to look down and send more data than they can at radio wavelengths, it will live on there. So I'd just like to thank you for your attention, and I hope that the exoplanets and the thousands of planets out there will inspire you to think about our own planet in perspective. Thank you.